All right, let's talk about something that's, well, literally right under our feet. Soil. But we're not just talking about dirt today. We're going to look at it through an engineer's eyes. And trust me, once you see it this way, you'll never look at the ground the same way again. So, let's dig in.
So let me ask you something. What's the real difference between dirt and soil? I mean, to most of us, it's pretty much the same thing, right? It's just the stuff you track into the house. But if you're a geotechnical engineer, the person designing a skyscraper's foundation or a massive dam, well, to them, that difference is everything.
See, here's the thing. An engineer doesn't see a single substance. They see this incredibly complex three-phase material. It's a mixture of solid particles, water, and even air, all existing in this delicate balance. You could almost say dirt is just soil in the wrong place. For an engineer, soil isn't just ground. It's a building material. And if you're going to build something huge and heavy on top of it, you can't just guess. You absolutely have to measure this balance. You have to put numbers to it. You have to predict how it's going to act under pressure. And that all starts with understanding these three components: the solids, the water, and the air. But how do you even do that? How do you take this kind of messy three-part system and turn it into something you can actually use in your calculations? Well, engineers have a single incredibly powerful tool for this. We're going to call it the master formula. Okay, before we just throw the formula at you, let's meet the key players. Think of these like the stats on a character sheet for any given patch of soil. First up is GS. That's basically how dense the solid bits themselves are. Then there's E, the void ratio, a fancy way of saying how much empty space is packed in there. S is the degree of saturation. Is that empty space full of air or water or a bit of both? And finally, the unit weight of water, which is our trusty benchmark for everything else. So the whole goal here is to figure out something called bulk density. This is the big one. This is the real world, as-is density of the soil out in the field, with all its solids, water, and air mixed together. It's simply the total weight of a sample divided by its total volume. So where does this master formula come from? Well, it's actually pretty logical. You start with that simple definition we just talked about, weight over volume. Then you cleverly start swapping in those key terms we just learned, the G's, the E, the S. You do a little bit of mathematical shuffling to connect them all, and boom, you get one single, clean formula that does it all. And there it is, the master formula. Just look at it for a second. Every one of those variables we just talked about, G's, S, E, they're all in there, working together. This one elegant equation ties together the particle density, the empty space, and the water content. It's the key that lets an engineer figure out the exact density of soil anywhere. It's so incredibly powerful. Okay, so we've got this awesome formula. Now let's have some fun with it and see what it can really do. Because where it becomes a real game changer is when you look at the extremes, the two most critical scenarios for an engineer: bone-dry soil and totally waterlogged, saturated soil. So let's play the what-if game that engineers love so much. What do you think happens to our big formula in those extreme cases? When we go from a parched desert to a soaking wet swamp, how does the math change? Well, here's the magic. On the left, you've got dry soil. In this case, the saturation, S, is 0. There's no water. So that S times E part of the big formula, it just disappears. It becomes 0. And you get a much simpler formula. Now look over on the right. Saturated soil. S is now 100%, or just the number 1. So the S basically drops out. And again, the formula simplifies, but in a totally different way. Just by plunging in a 0 or a 1, we get these two incredibly useful special cases. All right, so density is great. It gives us a snapshot of the soil right now. But what happens when things change? What happens when it rains or when a drought hits? This is where we have to talk about something called soil consistency. It's not just about what the soil is, it's about what it can become. Consistency is basically just an engineer's word for firmness. The best way to think about it is with a piece of clay, right? When it's totally dry, it's hard, it'll break. Add a little water, and suddenly it's workable. It's plastic, you can shape it. Add way too much water, and what do you get? A soupy liquid mess. That whole journey from hard to liquid, that is consistency. So let's do a little thought experiment. Imagine we have a cup of totally dry, powdery soil. We're going to go on a journey with this sample, and we're just going to start adding water, drop by drop, and watch what happens. So you start adding water, and at first, something really fascinating happens. Or rather, nothing happens. The total volume of the soil doesn't change. Not one bit. Why not? Well, that water is just sneaking into all the tiny little air gaps between the soil particles. It's like pouring water into a glass full of marbles. The total volume doesn't really go up until all that space between the marbles is completely full. But then you get to this one critical moment. The exact point where that very last little pocket of air gets pushed out and replaced with water. That is a huge tipping point. Engineers have a name for it: the shrinkage limit. At this exact moment, the soil is perfectly saturated, but it hasn't started to swell up. Not yet. Because now everything changes. All the empty seats are taken, right? So any extra water we add from this point on has nowhere to go. It has to physically start pushing the solid particles away from each other to make room. And that is the moment the soil finally starts to expand and its volume begins to increase. This whole journey takes our little soil sample through 4 distinct states of being. It starts out as a solid, dry, and brittle. Then we hit that shrinkage limit, and it moves into a semi-solid phase. Keep adding water, and it becomes plastic. This is its modeling clay phase. And if you just keep on adding water, you eventually cross the liquid limit, and the soil basically turns into a fluid. It just flows. And you can feel the difference in each of these states. Solid soil, it'll snap if you try to bend it. Semi-solid, it'll crumble in your fingers. Plastic soil, that's when you can roll it into a little snake without it breaking apart. And liquid soil, well, that'll just run right through your hands.
Okay, this is all really cool theory. But so what? Why does any of this actually matter? Why do engineers obsess over these formulas and these different limits?
It's because these numbers are everything when it comes to predicting the future. They tell an engineer if the ground under a giant building will stay strong and stable, or if a change in the water table could turn that ground into something dangerously close to a liquid, causing a total foundation failure. It's all about predicting how soil behaves when you put something heavy on it. And really, that's the bottom line. This isn't just a science experiment. Understanding the density and the consistency of soil, that is literally the foundation of safety in civil engineering. When you get this right, you prevent catastrophes. So the next time you're walking down the street and you see a huge skyscraper or you're driving over a long bridge, just take a second. Think about the incredible, invisible science that's happening right underneath it all. That careful, precise balancing act of solids, water, and air. I bet you'll think about the ground beneath your feet just a little bit differently now.